So I'm going to just explain how to fill in the spreadsheet that shows the distribution of inorganic carbon in fresh water. You've got a version of this that looks like this. So you've got the equilibrium constants for the dissociation of carbon dioxide in water. These are the equations. These are the equilibrium constants, and these are the log equilibrium constants. I'm going to use those in order to populate this table. So start with the law of mass action. We've got the equations, got this column which is the CO2 concentration. That's the atmospheric CO2 concentration which you're given, which is 10 to the minus 3.5. This table is all filled in with logarithms. So the concentration is 10 to the minus 3.5. So the logarithm of that is minus 3.5, the base 10 logarithm. And that atmospheric concentration of CO2 is constant regardless of the pH. Okay, so the pH we've got listed between 2 and 14, going up in half pH units, and we want to see the effect of pH on the distribution of these species of inorganic carbon. So the CO2 itself, H2CO3, HCO3 minus, which is bicarbonate, and CO3 2 minus, which is carbonate. So we can fill in 10 to the minus 3.5, so 3.5, and copy that all the way down because the carbon dioxide concentration in the atmosphere is unaffected by the pH. Next column is H2CO3. We've got the equation there, CO2 gas plus water gives you H2CO3, and the equilibrium constants 10 to the minus 1.5. So what that means is if we put the product divided by the reactants, in this case the product H2CO3 and the reactants CO2 and water. Water, of course, we don't count, or it counts as 1. So we put H2CO3 concentration divided by CO2 concentration equals 10 to the minus 1.5. Then if you were to take logarithms of both sides, that would change from being H2CO3 divided by CO2 into being H2CO3 minus log H2CO3 minus log CO2 equals log of 10 to the minus 1.5, which is minus 1.5. So we've got log H2CO3 minus log CO2 concentration equals minus 1.5. So we want to get H2CO3 on its own on the left hand side, so we just need to move the minus log CO2 onto the right hand side. And if we click on the equation that's written there, you can see that's what we've got. What we're working out is the log H2CO3 concentration, and that's equal to log KH, which is minus 1.5, plus C9, which is the CO2 concentration, the log CO2 concentration. Okay, and then that's copied all the way down, and again you see that the H2CO3 concentration is unaffected by the pH. You can tell that because in the equation there's no H plus written in there. It's not affected by the acidity. So the first two columns are straightforward to fill in. The first one is just 10 to the minus 3.5, so it's minus 3.5 copied down. Second one, we do the law of mass action. We've got the equilibrium constant. They turn it into logarithms for ease of use, and then just rearrange it. Okay, and then bicarbonate. We've got the equation for the first dissociation of H2CO3. So H2CO3 dissociates to give you an H plus and an HCO3 minus. The equilibrium constant for that is 10 to the minus 6.3. So if we again look at the law of mass action, the products are H plus and HCO3 minus. So if we multiply H plus and HCO3 minus, and then divide by the reactants, which is H2CO3, then that will equal 10 to the minus 6.3. So products H plus times HCO3 minus divided by reactants H2CO3 equals 10 to the minus 6.3. Then if we take logarithms of both sides, so we have log HCO3 minus plus log of H plus minus H2CO3 rather than dividing by, so minus the log H2CO3 equals the log equilibrium constant, which is minus 6.3. So we have log HCO3 minus plus log of H plus minus H2CO3 equals minus 6.3. We need to rearrange that, so we have HCO3 minus log HCO3 minus on its own. To do that, we end up with log HCO3 minus equals minus 6.3 plus H2CO3 minus H plus. Now remember, pH is the negative log of the hydrogen ion, so minus log H plus is the same as plus pH. So again, if we click on here, the formula that we've written in there is minus the log equilibrium constant, so the bicarbonate concentration, the log HCO3 minus concentration equals the log equilibrium constant, which is minus 6.3, plus D9, which is the log H2CO3 concentration, plus the pH, the pH being the minus log hydrogen ion concentration. Okay, so that's where that's come from. And if we move on to the carbonate, which is from the second dissociation, where the HCO3 minus dissociates to give another H plus plus the carbonate. The equilibrium constant for that is 10 to the minus 10.3, so a very small number. Again, if we go through the law of mass action, we've got CO3 2 minus carbonate multiplied by H plus, they're the products, divided by the reactant, which is HCO3 minus bicarbonate, equals 10 to the minus 10.3. So the reaction doesn't proceed very far to the right, only a tiny amount. So that's carbonate concentration times hydrogen ion concentration divided by the bicarbonate, which is the reactant, equals 10 to the minus 10.3. Again, if we take logs of both sides, we end up with log carbonate concentration plus log hydrogen ion concentration minus log bicarbonate concentration equals the log equilibrium constant, which is minus 10.3. So to rearrange that, we need to get the log carbonate concentration on its own, so we need to move the hydrogen ion and the bicarbonate to the right hand side of the equation. So if we move those across, we end up with log carbonate concentration equals log bicarbonate concentration minus 6.3 minus H plus. Minus H plus is the same as saying plus the pH, because the pH is the negative log of the hydrogen ion concentration. So here's the cell for the log carbonate concentration. We've got minus 10.3, which is the log equilibrium constant, plus B9, which is the pH, plus E9, which is the bicarbonate concentration. So if we copy that in there, then we can copy that down, and we can see that both the bicarbonate and the carbonate, these concentrations do change with the pH. Not surprisingly, because the equations contain an H plus, so H plus is part of the equation. So the log bicarbonate concentration goes from pH 2, it's 10 to the minus 9.3, which is a very, very small amount. And as the pH increases, the concentration increases. And that's what we're showing on this graph. Carbonate and the bicarbonate. Those are graphs of positive slope, so concentrations increasing with the pH. pH is on the x-axis. The H2CO3 minus is unaffected by pH, and so is a straight line of zero slope. So that's a graph that you can expect to see in a textbook, which shows the concentration of these inorganic species with change in pH. The other graph here is drawn from looking at the ratios of these. In order to work the ratio out, first of all we need to work out TIC. TIC stands for total inorganic carbon, so that's the total concentration, and that's worked out by taking each of these log concentrations and turning them back into actual concentration. To do that, of course, if the log concentration is minus 5, then the actual concentration is 10 to the minus 5. So that's what we've got here. 10 to the minus 5 plus 10 to the minus 9.3 plus 10 to the minus 17.6. And that's the total of the inorganic carbon concentration. So if we have the total, then if we divide each of those species, so this is the H2CO3, 10 to the D9, that gives you the concentration of the H2CO3 divided by the total, and that'll give you the proportion of inorganic carbon that's present as H2CO3. Similarly, for the bicarbonate, 10 to the minus 9.3 divided by the total, and then again for the carbonate. And again, that's plotted in this graph, and it shows the shift in inorganic carbon speciation. At low pHs, most of the carbon is in the form of H2CO3. As the pH increases, we get more and more of the carbon being in the form of bicarbonate. And around the pH of most natural waters, which are slightly acidic but around neutral, so between maybe 5.5 and 8, largely we've got bicarbonate as the predominant form of inorganic carbon, and then at higher pHs you start to get carbonate becoming dominant.